Okay, so we're going to talk about bubbles that we make on gold nanoantennas. So thermoplasmonic bubble nucleation. And the presentation is based on basically 3 papers. 2 that were led by my former PhD student, Stephen Jones. The ones that are shown to the left here. And a recent paper by my current PhD student, Pantea Dara, who's also here. He's there. Say hello to the audience. So I will start by sort of introducing the first 2 papers as much as I can remember of them now, because it was some time ago. And then Pantea will talk about the last paper. And then we end up with some hopefully open questions that would be great to discuss with the audience. So that's the plan. And we have half an hour in total, right? Something like that.
Yes.
Yeah, great. Thank you. All right, let's see. Can I move this thing so I don't see this? All right, so these thermoplasmonic bubbles, the idea is to be able to use them as some kind of active manipulation elements for generating flows. And that could be in the context of microfluidics, where you want to mix things very fast, for example. I mean, it's usually difficult to generate flow, and particularly locally. And one of the big needs for doing that is to, for example, in the sensing context, is to be able to mix different molecules or pull molecules to a sensor surface in an efficient way, much more efficient than what can be achieved by passive diffusion. And this type of research has been going on for some time. So I just show an example here from a recent paper, or fairly recent paper, where one have bubbles that pull in thermoplasmonic bubbles that pull in molecules to sensing structures, and one measures SERS, surface enhanced Raman, from them, because the molecules are pulled in towards this to the underlying gold structures that also in this case generate this bubble by laser heating. So this is a fairly general idea. We haven't really done any sensing experiments so far. But the objective has been to do that. We'll see where it ends. Nevertheless, the whole phenomenon here is about basically generating flows through a Marangoni effect, or an effect that is related to Marangoni effect. So when you make a bubble, you have gas and you have liquid on 2 sides of an interface, which means that you have a surface tension on that interface. And since this bubble is created by, or the heat that generates the bubble is created on one side of the bubble, there will be a thermal gradient on the surface. So there will be a surface tension gradient, and that surface tension gradient in turn will drive flow around the bubble. And that's what indicated in this picture to the left there. So that's the phenomenon that we want to look at. And this phenomenon has been researched for several years. I show some results here from another speaker. I saw Kyoko Namura, who will present, I think, here in this seminar series in a couple of weeks. So she's done a lot of research in this area. And one of the conclusions from this work is that to really generate a strong flow, you need to make a small bubble. So a small bubble obviously will have a more pronounced thermal gradient on its surface. So because of that, it will generate a stronger flow. Now that's illustrated in these 2 graphs to the right here. where in one case there is a small bubble, and the flow is here seen by tracer particles that swirl around the bubble. And you have a much more pronounced flow than in the case where you have a large bubble to the left. Now, the large bubble in this case is what happens if you use ordinary bubbles and a large heating structure. For example, you just take a diffraction limited laser spot and illuminate a continuous gold particle surface. So then it'll be the laser spot itself that basically determines the heated surface area. So the bubble will be large. And if you have ordinary water in this your liquid, then gas will flow into the bubble that you create, and the bubble will grow and grow, and that will then decrease this surface tension gradient in the end, resulting in a pore flow. So what she did before is to use degassed water and remove as much gas from the water as possible, and that in that case will restrict the bubble growth so that you can have these strong flows because you have a small bubble. But of course, in many applications, it's not very useful to use degassed water. Maybe you want to use this with just flowing in ordinary buffer or something, or some kind of test sample in a microfluidic device that's equipped with this kind of plasmonic heating structure. And then you want to be able to still generate a strong flow through exciting small bubbles. So that's what we wanted to do, and we did that by instead using small structures that we nanofab. So we make small structures consisting of gold nanodiscs. Okay, there are several nanodiscs in an antenna patch. Each nanodisc have basically the same size most of the time. And they're usually circular, like you see here. Now, the distance between these disks are so large so that it doesn't really matter how many you have. They have more or less the same optical properties, irrespective of their number. They're not near field coupled or anything like that. So the absorption properties are the same, which means that basically it's the overall number of gold disks in the structure that determines the total absorption in the antenna patch. So by restricting this number, restricting the heating size in this way, so that it's the antenna patch rather than the laser beam spot size that determines the amount of heat, then we can still generate small bubbles. And when you have such a small bubble, it turns out that the size of the bubble doesn't increase with time, even if you have ordinary water. Okay, and the interpretation is that it's a self-terminated growth basically here because of the Laplace pressure. And we have estimated the bubble size that we generate by these different sizes of antenna patches, and it basically matches is proportional to the size of the antenna structure, as you can see in the lower right graph here. We heat the bubbles, we generate the bubbles using 532 nanometer laser light, which is done in more or less resonance with the plasmons and the gold nanodiscs. You can see the absorption, or actually the scattering spectra to the left, and the lower left graph here. And the absorption profile is more or less the same as the scattering profile in this case. So that's the system that we use to heat. And we then investigate the bubbles and the effect of the bubbles in two ways. So first we excite the bubbles, actually not by a continuous wave illumination, but by modulated heating, by modulated irradiation. So we have a square wave laser beam that comes in, square wave modulated laser beam that comes in. And we can regulate, of course, the power of the beam, but also the frequency of the modulation. It's a 50 bright and dark time in this heating beam. Okay. So we can modulate. We can then look at what happens on the in the bubble region by having a reflected or transmitted low power red laser beam that goes through. By looking at the backscatter or forward scattering of that beam, we can see if a bubble is created or not. And the graph to the right here shows the what one can see then. So as a bubble is created when the laser, so we turn on the bubble at t=0, and the bubble is immediately created, basically below our resolution, time resolution here. So very fast generation of a bubble. And then when the heating is turned off, then we see that the bubble signal, the transmission of this red laser beam, is gradually fading away. And by looking at that intensity decay here, we can say approximately how long it takes for the bubble to disappear from the small heating structure. So we have a fair idea of what's happening in the bubble region, what is the dynamics of the bubble, so to speak. But then, of course, we need to measure the flow that's generated by the bubble as well. And then Stephen, he developed an holographic optical tweezer system that allows us to do force microscopy. So we trap a polystyrene bead in the liquid, in the measurement chamber, and we look at the displacement of that bead to measure the flow that's induced by the bubble. Okay, so we can do, and we can of course measure that then in 3 dimensions. So we can do a 3-dimensional flow velocimetry near to the bubble. So this gives us a handle to both probe the bubble dynamics itself as well as the flow that's generated by the bubble. So this is an example of what we can see. So to the left, you can see vectors giving the flow, and they both have direction and they have a size, okay, or a magnitude. It's in millimeter per second, and the distance here from the bubble is a few microns. And you can see that we have very large flows. We can also model that flow in a similar way as Namura did in some of her work by a model called a Stokeslet. It's basically it's the simplest model for this kind of flow, for a Marangoni flow. And we can see that the flow pattern that we generate by this bubble is in a good agreement with this Stokeslet picture. Okay. The flow speeds that we record, the average flow speeds that we record is typically of the order of 100 microns per second. But it turns out that it varies a lot in time. Okay, so if we look at the flow just after this bubble has been induced, just after a bubble has been nucleated, then we see a very, very strong flow transient. So this can be seen here in this pictures here. So this is with 2 different laser powers. The first one, 10 milliwatt here, is just above the threshold for bubble generation. So much below that, we don't generate a bubble at all, right? But at 10 milliwatt here in this case, 10 milliwatt 532 nanometer laser, we generate a bubble. We can look at this we can see the bubble generation by monitoring the transmission of this red laser beam. That's the red signal here. And we can see that the bubble is generated there. And we can also monitor the flow. And you can see that there's a peak coming up here just when the bubble is created. That peak becomes even more pronounced if we increase the laser power a little bit more. We get a very strong transient here. And that is magnified here again. So here we see this strong flow transient. And in this case, transient flow speed near the bubble can be up to millimeters per second in speed. However, we can do this velocimetry using this holographic tweezer technique as well. And we see then that the flow profile is the same as irrespective of time. So it's the magnitude of the flow that changes with time. It's not really the directions. Okay, that's the same flow profile as predicted by this Stokes-Lett model. Now, this transient flow, it decays, of course, as you go out from the surface, just like the average or this more usual Marangoni flow. Decays out from the surface as approximately as 1 over r to the power of 3. And it also then decrease in magnitude with time after the nucleation event. But the profile is thus the same, or irrespective of time. Now we can also then, as I mentioned before, we can monitor the decay time of the bubble, and we can see then that these strong flows, this strong flow transient, they do not exist if the time between these heating sequences, if the dark time between the heating sequences is shorter than the decay time of the bubble, the dissipation time of the bubble. So if the bubble survives the dark time, meaning that there is no new nucleation event, there is already a bubble there, then we don't see this strong flow transient. And so obviously that time depends then on how we modulate this heating pattern, okay? And it turns out, depending then on the size of this antenna patch, that there is a fairly distinct threshold modulation frequency for when we induce this strong transient. Okay, now I went too fast here. So in this case, for example, we have this strong flow transient here up to a modulation frequency of about 100 Hertz. After that, we just have an ordinary Marangoni flow because there is always a bubble on the gold patch, and the flow speed is then much lower. Okay, so the transient peak disappears if there is no nucleation event. To summarize this thing, we can make these smaller and fast. We can make small bubbles, and they can generate strong flows, in particular within this nucleation time, sort of just after the nucleation of the bubble. And we can modulate. We can produce these transients with a high modulation frequency, with a high frequency. Which depends then on the size of the gold patch that we use. If we use a small heating patch, like just 1 nanoparticle or 3 nanoparticles here, then they can be generated with several kilohertz. If the patch is larger, then it takes longer for the bubble to disappear because it's larger from the start, and then we can it's in the 100 Hertz regime. Right. So, but what this implies is that we have a system then for both generating and controlling flows in very confined environments, and also with a very high dynamic rate. But what we don't show here, or what we have not addressed here, is that the direction of the flow. We have not controlled the direction of the flow. The flow is always given by this, the flow pattern is always given by this Stokes-Lett model, meaning that it's directed towards the bubble at the substrate surface, which is, of course, the most interesting area for example, putting sensors. So in the next study we did, which Pantea and I will present, we tried to actually generate a directed flow or change the direction of the flow by making other types of constructs. And I give the word to you now how to present them. Yeah, see here what time. Okay, please.
Okay. So in continuation of studying these transient flows, as Mikael mentioned, we decided to study whether if it is possible to change and dynamically control the direction of this flow around our bubble. It has been previously shown that it is possible to change the direction of flow around microscopic bubble with different methods. The basis of all of these methods were the same. So basically, when you have a single heat source and a bubble on top of that, you have this out-of-plane temperature gradient, which create this flow that go to the top and return and go to the heat source on the surface. But if you break the symmetry of your temperature profile and make your bubble warmer on one side, then you will create this directional flow that in the bulk go from the warmer side of the bubble to the colder side. So Nomura has done two different methods for create such directional flows. One of them was that she used two laser spots on top of a gold nanofill. The laser spot with a larger power was responsible for creating the bubble, and the one with lower power was responsible for creating this temperature profile. So one side of the bubble would be warmer, a directional flow would appear from the warmer part to the colder part. She also used an isolated structure with different absorption at each side of it. So when the bubble is created on top of this isolated structure, the part with higher absorption will be warmer, the part with lower absorption will be colder. So this in-plane temperature gradient will again induce this directional flow going from the warmer part to the colder part. So what we decided to do was to use two array of nanoantennas and put them beside each other, which differ in size and polarization. We chose the size of these arrays and the distance that they should have from each other experimentally. We finally decided to use our primary array of nanoantennas consisting of 19 nanodiscs, and the secondary nanoarray consists of 7 nanodiscs and make them 2 micrometer apart from each other. When we do the measurements, we see that in higher planes in the bulk, we will have the directional flow that we expect from where we expect to be warmer to the colder. But as we get closer to the surface, we saw a substantial component directed away from the nanoantennas, which it means that around the nanoantennas, the particles were pushed away. To study this flow pattern, we again use the Stokes-led simulations. So Nomura again has shown that it is possible to simulate directional flow using this tilted Stokes-led. So for a bubble with a temperature gradient parallel to the z-axis or out-of-plane temperature gradient, you can simulate your flow using a Stokes-led parallel to the z-axis. But if you have if you have in-plane temperature gradient as well, then you have to tilt this Stokes-led. And then we realize no matter how much we tilt it, we are not able to produce a flow that is matching with our flow profiles unless we use two tilted Stokes-led into opposite direction in the position of our nanoantennas, which makes us realize that we have two bubbles when we are illuminating our structures. To make sure that is the case, we also did an FEM simulation using realistic photothermal heat source densities, bubble sizes, and surface tension coefficient. And our FEM simulation also matches very well with the experiment and Stokes-led, indicating that we have two bubbles in our experiment. The only thing that we had to take into account was that we have to shift the center of the bubble toward the outer edges of nanoantennas, which it means that upon nucleation, the bubbles also were moved toward the predicted direction. And then we decided to study the effect of transients on the total displacement of particles that we have on the surface close to the nanoantenna. So we have these free particles on the surface, and we start illuminating our nanoantennas and measure the total displacement as the probe particle get away. And we saw that up to 100 Hertz, we have an increase in the total displacement, and after that, there is a little decrease, which indicates that when our bubble is not able to vanish, so we don't have the nucleation phase, the total displacement won't anymore increase, and the transient response is responsible for huge and fast displacement of particles on the surface. To model that, we model the change of velocity with an transient peak that decreases exponentially and finally converge to a persistent flow. And at each cycle, we calculate the total displacement based on our fitting numbers. And as you can see, the total displacement that we get by the model on the bottom, it matches very well with the experimental result that we have on the top of the screen. So again, that was another indication that the fast displacement of particles on the surface, which the no-slip condition exists, is due to the transient response. And then we decided to study whether it is possible to dynamically change the direction of the flow. And for that, we use elongated structure, this ellipsoidal structure for heating. So they use as a switch for turning off and on our heat source. So our primary structure is still circular. It will always create a bubble. But our secondary structure now only gets heated when the polarization of light is parallel to the long axis of the ellipsoid, and it's turned off when the polarization of light is perpendicular to the long axis of the ellipsoid. On the right side of the screen, you can see that the flow pattern created when the polarization of light is parallel to the long axis direct the flow toward outward, and when the polarization of light is perpendicular, the flow come inward and close and toward the heat sources. So we were able to dynamically control the flow around the nanoantennas with polarization. So in summary, we were able to induce transient flows and direct them using in-plane temperature gradients. We were able to show that this transient flows are strong enough to move the beads on the surface for tens of microns in just few seconds. And we were able to dynamically control the flow using the polarization. Now, the questions that we are trying to answer is that what is the precise nature of the flow transients? Because although we know that it is dependent on the nucleation of the bubble, but there are questions like if it's like kind of a shock wave, or if it is not, how it can be directed, because the shock wave cannot get directed somehow. And we also want to know how the nanostructure and material of heating sources can affect this bubble nucleation. Can we create like faster, even transient flows if we change the structure? And is there any self-oscillation when the bubble is created? Because we are not able to observe or measure it if it's happened. Yeah, and it is that. Thank you for your attention. And
thank you.
Thank you very much. We have to thank you for the very nice presentation of generating bubbles and these flows, these strong flows. There have been already several questions in the chat. Maybe I give the chance to 3 people to ask directly the question, or should I read them? I mean, how you want to do that? I mean, I can also read that, but
I can read myself, or we can read here. So Michelle, you ask about is the transient due to boiling? How fast is it? Well, I mean, the transient is due to it happens when the bubble is nucleated, right? So in that sense, I guess I would call that boiling.
Okay, I was wondering whether, at the beginning, is it purely a water, steam, water vapor, or already air is coming in? while the bubble is growing? I mean, it's probably not possible to know.
We
but,
can't measure that because I mean the bubble, as far as we can see, the bubble appears as soon as we turn on the laser, sort of as soon as the laser part starts. We cannot resolve any dynamics.
But your
there,
resolution
really.
is what, a millisecond or microsecond?
Yeah, it's like millisecond maybe.
Okay.
What's well, I mean, what is the time with what time resolution can we resolve how fast the bubble appears?
Oh, less than
Milliseconds.
Okay, millisecond. Yeah, of course. I mean, in principle, you would expect tens of nanoseconds or 10 nanoseconds. I mean, it's very, very fast if it is boiling, right?
Yeah, I mean, we think
air
that
diffusion,
we think that this nucleation induced flow happens before any inward flux of gas to the bubble. I mean, it seems reasonable.
So it should be boiling. Yeah. Okay, thank you very much.
Okay, thank you. Let's see here. Lisa asked, what kind of temperatures do you have in your experiments and how do you measure them? Well, the easy answer is we don't measure the temperature. Okay. Then of course we know from other works that, you know, what kind of temperatures do you actually have to induce on the surface of a gold nanoparticle to induce a bubble, and it's usually way above 100 degrees Celsius, right? It's typically maybe, what is it, like maybe
It's about
200 degrees Celsius or something. So that's probably where we are. We have in this study, we have not attempted to measure that. We have done that in some other studies, but not here.
There was Julian before. Is there also a transient flow when the bubble bursts? Does it have?
Okay. Yes, I missed that. Okay. Yes. No, we don't see that. No.
Mm-hmm.
So it seems that we get a transient when we induce the bubble. Then the flow, you know, the flow that we see, or the bubble signal, is decaying basically exponentially to some level where it's more or less persistent. And if we turn off the laser, then it simply just dissipates and disappears. There is no new sort of transient, let's say, in the other direction there. Yes. And
there's a third question, or the last question. Maybe if you quickly answer that, we could even take that, and then you only have my question.
Yeah, so Falco, you asked about the spatial resolution of the velocimetry technique. So I give that to you, Antea.
Well, we cannot get closer than 8 micrometer to the nanoantennas because the flow is so strong that it's pushed out the bubble from the trap. And then after 12 micrometer as well, the trap become too weak based on our setup. So we are able to move something between 8 to 12 micrometer, but like every half a micrometer to measure the flow.
And resolution, I guess, I mean, it's what could it be here? I mean, how precisely can we determine position?
The position,
I think
very like 0.1 micrometer.
Yeah, okay. Yeah, something like that, maybe. Yeah, a couple of 100 nanometers,